Hi, video number 19. So in this video I'll explain to you how to construct an autonomous set. How to construct an autonomous set. We call it as a gram-schmidt process. Gram-schmidt process. The purpose is to construct the autonomous set. Okay, so now let's say we were given a set of function f1, f2, and so on, fn. Okay, given set of function, then we want to construct, then we can construct an autonomous set So let's call that set as a G1, G2 to Gn, and so on. Okay, using the what we call as a gram-schmidt process. Now the step is as follows. I will explain that. First, so we take G1 as f1 over norm of f1. Okay, and then next, to define G2. In order to find G2, we define, let's say W2 of x as f2 x minus f2 G1. Okay, so here W2 is orthogonal to G1. In this case, W2 is orthogonal. W2 is orthogonal to G1. Then we construct having defined W2, we find what W2 is. Then we can find or define G2 as W2 over norm of W2. Okay, so we have G1, we have G2, then the process continues. If we want to find G3, then we need to define what is W3. W3 is F3 minus, here we need say F3 G1, I think I put it big bracket there, G1 plus F3 G2 that, and then we define what we can find G3 by omega W2 divided by norm of W, sorry, this is 3, W3. The process continues. So if we go on up to, we want to find up to Gk or Gn, so we need to define what Gn is. Define Wn as, let's me use k here, Wk. So Fk minus, here is summation. So summation of, we have Fk Gi, where I from 1 to k minus 1. And then we can find, we can have Gk as a Wk over norm of Wk. So this is the process. This process we call it as a gram-schmidt process to define or to construct the autonomous set. Now, if f itself is orthogonal, if itself is already orthogonal, if the given set here f n is already orthogonal, then to construct the autonomous basis, the orthogonal set of function is easy. Then for to construct Gn, which is orthonormal. So what we need to do is just we consider G1 as f1 over magnitude norm of f1, G2 f2 norm of G2, and so on. Dk fk over norm of gk, fk. This for the case of f is orthogonal. Else, if not, then we need to follow the gram-schmidt process. We need to do all these things. Alright. Now, okay. Now let's starting from the an autonomous system, arbitrary autonomous system. So it is possible to construct the theory of Fourier series. The theory of Fourier series. Suppose we want to find. So let me write those things. Suppose we want to find the best approximate the best approximate approximation of an arbitrary function fx in terms of linear combination, in terms of a linear combination of an autonomous set, linear combination of an autonomous set of an autonomous set. Let's say G1, G2, G1, G2, Gn. Okay. So, which means here we say approximation means we need to choose a coefficient alpha 1, alpha 2, alpha n such that we minimize f alpha I gi squared 1 to n. Okay. Now for arbitrary constant, constant alpha 1, alpha 2, alpha n, we have norm of f minus alpha I gi I from 1 to n, that you expand that, this will give you f squared plus f of gi minus ai squared, yeah, a we define a later on, minus this is I from 1 to n, sum I from 1 to n fgi squared, where ai is the inner product of f and gi. Yeah. So here in this case, the ai is known as this ai is known as is a Fourier coefficient. Yeah, Fourier coefficient of the function fx relative to the normal autonomous system gi. Yeah, relative to the autonomous system gi. Okay, so let's see some of the example on how can we develop or how can we construct the autonomous system, autonomous set. Yeah, example. Let's say we have this set of function cos nx for n any 1 to 3 up to whatever. Yeah, orthogonal on the interval. Show that the set orthogonal on the interval. So let me show that this orthogonal on 0 to pi, and find the corresponding autonomous set. Alright. So in order to show they are orthogonal, we need to use definition of orthogonal, apply the inner product of those things. Right. So of course, for the orthogonal, we need this relation 0 pi f1x f2x dx equal to 0. You need to show this. Then if you can show that, then we can say should be ij here. Yeah, for I different than j. Now, so in order to do this, we let let's say f1x as a cos mx. Yeah. Use the definition. This is the set of function given, and if you take f2x as cos nx for m different than n, so then we apply that. We have 0 to pi, because the interval under consideration here is 0 to pi. Alright, so 0 to pi f, let's say this f1 f2, so f1 f2, so we have cos mx cos nx dx. So you can show that you can either use a identity, the required identity, you can do that, or you can also use a integration by parts. For the integration by parts, I think you need to do twice. Yeah, I think you need to do twice. Then you can get this, that give you 0. Okay, so therefore it is the orthogonal. So therefore cos nx is orthogonal. Now you need to construct the orthonormal. Yeah. We need to construct the orthonormal. So let's do that one. So to set, first we need f naught, yeah, f naught x. Let's say f naught x. This is considered as a cos 0. That give you 1, magnitude of 1. That's a norm of 1. And use the definition of magnitude, definition of norm. We have this is just integrate 0 to pi 1 squared dx to the half. Okay, this is the definition of norm. This is equal to pi, yeah, square root of pi. This is for x equal to 0. Yeah. Then for x different than 0, we have fn x. This is cos nx. Alright, if you find norm of that, that will give you integrate 0 to pi cos squared nx dx to the half. Okay, of course you can solve this. You can use the appropriate identity for cos squared, so that gives you sert pi over 2. Yeah, so now we have, from there we have f naught, for f naught equal to 1. So sorry, yeah, for f naught equal to 1, yeah, we have f naught equal to 1. The norm is given as sert pi, and then for n is given as fn is given cos nx. We found the norm of that is given as that. Yeah. Now we need to find g, set of g. Yeah. Now to find g, let's say gi. So we have g1 is equal to f naught over f1, f naught, norm of f naught. So we have 1 over sert pi. Okay, and then for gn, we have fn. Now if gn is fn divided by norm of fn, that give you norm of 1 over that is sert of pi over 2. So inverse, we have sert 2 over pi, and fn is cos nx. Okay, so therefore the autonomous set is, we have g and x. This is given as first 1 over sert pi, and then second 2 over pi cos nx, and then you can proceed. Next you got 2 over pi cos 2x. Sorry, this is cos x, cos 2x, and so on, because gn is cos nx. So just this is for g2, this is for g0, g1, g2, and so on. Okay, I'll give you another example. Show that the set of function, sin n pi x over c is orthogonal on interval 0c, and normalize the set, and normalize the set. Again, we use definition of orthonormal. We use definition of orthonormality. So we have, I think this should be 0 to pi, not 0 to c. Okay, so first to show the orthogonal, we use the definition of those 0 to pi sine n pi x over c sine n pi x over c dx. Again, you can show this is equal to 0, therefore it is orthogonal. Yeah, so therefore those set is orthogonal. Okay, now to normalize the set, Fn norm of Fnx, yeah, this is norm of our Fn is sine n pi x over c. Okay. This is integrate 0 to pi sine squared n pi x over c dx to the half. Okay, if you do this, you got c over 2. Hence you can find the orthonormal set Gnx is given as you need to normalize those. We have sine n pi x over c over norm of sine n pi x over c. Yeah, so that give you 2 over c sine n pi x over c. That's the orthonormal set. Okay, and we have another example in the notes, but I think you can just study that one. So with this example for the orthonormal, or how to construct the orthonormal set from the given set of function using the gram-schmidt process, and that example I stop here for this video. Thank you.